when we look at the next couple chapters, what we're going to see is we're all conceptual. Now, that's a whole different ball game in terms of how you prepare. So it isn't memorizing a step to solve a problem, like naming, and particularly might be get confused. Do I use the ionic or do I use the covalent, and do I mix them up? Which is easy to do. But what we're going to do is we're going to describe how things happen on Earth. And so what you are going to need to do in terms of preparation for that is to be able to describe things. So an example, we're going to describe reasons why a cloud forms. And so, what should you be able to do? You should be able to sit down with somebody, like a roommate that's not taking this class, and describe the 3 ways a cloud forms. And they should be able to understand it. If you can explain what's going on or tell the story about how this happens, then you'll be prepared for the exam. And so this is being able to take the information and explain what's important or what are the key ideas about the process that we are. So cloud formation, we'll talk about how rain forms. We'll talk about what happens to the earth as the rain hits the earth. Where does the water go? And so we'll build context about this. And so we'll take a look for the next couple of classes. We'll look at the atmosphere and what happens there. We live in it. There is gas that we walk through. We don't really realize sometimes that it's there, but sometimes wind hits us in the face and we know it's there. This is where weather will occur, so we're going to talk a little bit about weather. You may see weather reports all the time, or you look at the Weather Channel app and you see data, but we're going to understand where that data comes from and what that might mean and how we might predict things from that data. And it's a generality, because this is kind of what meteorologists do. They take a look at the data and they try to predict. Sometimes they're right and sometimes they're wrong. And we'll look at that. Then we'll look at the Earth, what it's made up of, and what happens on the surface of the Earth, and we'll describe those processes. And so that's what we're heading towards. We're about ready to talk about the atmosphere and the hydrosphere. So, what in the world are we going to look at when we look at these 2 items? Well, let's first define them a little bit. The atmosphere is the gas layer that we live in. The things that we think about are rain, wind, snow, things like that are found. The hydrosphere is actually all the water on the surface of the planet, which takes up about almost 75% of the Earth's surface and everything below. One thing about the atmosphere that we know, we observe it. We are inside it. We walk through it. So we know a lot about the atmosphere, and we describe a lot of things. The hydrosphere, on the other hand, is very sparsely populated. We don't live on the ocean. We do sail on it, but we don't spend a lot of time, and there's not a lot of people who spend a lot of time underwater. So there's a part of the world that we know a little about, but we aren't as familiar with 75% of the entire surface of the Earth as we are with the 25% that we live on top of the Earth. So if there is an undiscovered country or a place to explore, under the water is where it would be. It is not as easy to get to and to be there because of the fact that we have to breathe. That's probably a really important thing. And so even though we do have submarines that go under and we do research, we have only looked at a very small, tiny fraction of that entire space. Now, the atmosphere is composed of a homogeneous mixture of gases. Uh-oh, I brought in a term from last time. Okay, it's got stuff, lots of stuff. It is not one thing. It's composed of every single gas that is represented on the periodic table, along with a whole bunch of other compounds that are gases that are in the air. Now, even though we have a mixture of a lot of different things, what are the 2 things that are dominant? nitrogen and oxygen. If you total those two up, it makes about 99% of everything. So the air is basically two major gases, nitrogen, the largest fraction, and oxygen, which is a much smaller, about little over 20% of it is oxygen. Now, the one thing that is important to us biologically is the oxygen. We breathe in air, nitrogen and oxygen gets into our lungs, but only the nitrogen is extracted for us to use. The nitrogen comes in, the nitrogen goes out. Nitrogen is really unreactive and it just floats around. It takes up a lot of the space, but is not as important for us in terms of immediate for our survival, although the nitrogen does feed plants' growth, and the nitrogen is still important. Then we have other things like argon, carbon dioxide, neon, helium, methane, krypton, and they're really, really tiny percentages. Okay, so they don't make up a lot of how much is there, but because of how large our atmosphere is, even a tiny, tiny percent makes up a big fraction. And so by chance, if I was offered 0.00015% of $1 trillion, I would say yes, because even a small percentage of a very big thing would set me up for life. And so even though they're small percentages, it's representative of a lot of stuff in the atmosphere. Sometimes it's hard to get to extract it, but it's there for us. That could be used. Yes?
With under hydrogen, the carbon monoxide, is that all just representative of the less than?
Yes. The last part of this grouping here, hydrogen, carbon monoxide, xenon, ozone, things of that nature, represent less than, if you total them all up, less than this percentage. And so they're not large enough to have a percentage of their own. But these are important things. If carbon monoxide gets too high in concentration, that's not good for us because it will block out oxygen and we will die. Ozone is important for us, and we'll talk about that particular gas, although it is a really tiny amount, but it is a huge thing for us. And so just because it's small in size doesn't mean that it's unimportant. Now, when I look at the atmosphere, there's one thing that is missing in this, and you can see it in the title, and you know what is missing if you just did your hair and you walked outside in the middle of summer. What is missing in this percentage? Water. Humidity. Okay? And so, why in the world do we describe dry air and not the air that we normally take in? Well, the humidity can change drastically. It can go up and down. And so if we wanted to give percentages, we take out the water because that changes a lot, and then we left with the things that don't change very much. And so we have a change in humidity every day. Enough so that even in weather reports, that's one of the items that is reported is the humidity because it changes. And that has an effect on us a lot of times. In the winter, when there's absolutely no humidity, what happens to your skin? It gets really, really dry. And if you walk out in the middle of summer, your hair doesn't keep up. Doesn't matter what you do to it. Too much humidity can take it down and make it not behave the way you want it to. I know, I have 3 daughters. Okay. Now, the atmosphere is interesting in that it is not uniformed. It isn't the same. Okay. It, near the surface, is really, really thick. And as I go higher, it gets thinner and thinner and thinner. Now, one thing weird about the atmosphere is this. There is no edge. Okay? It is like blending or shading, and you can have really dark shading, and then it gets lighter and lighter and lighter and lighter and lighter, lighter, lighter. And it gets just, it kind of fades away. But there's really no definite line where it says the atmosphere stops and space starts. Okay? So that's important to know. What holds the gas to the Earth is gravity. Just like why we are held to the Earth, gravity is pulling on us. So it is with the gas. but gravity affects it this way. It pulls it mostly close to the ground, and then little bits go really, really far away from us. And so what we do is we define different regions and we give them different names. And so the troposphere is the gas that starts from the ground and it goes up for 11 to 12 kilometers, depending upon what book you take a look at. And so this is where we live, we interact. This is where most of the weather actually occurs. Just about everything is there. The majority of all of the gas in the atmosphere is in this tiny area. Even though we have all these other layers, the amount of gas in the first layer, the troposphere, is so much more than what's spread out with the other layers. The next layer is the stratosphere. You might have heard of that, up in the stratosphere, meaning most people think about that as being very, very high. And so we go up to about 50 kilometers at that moment in time. The next phase is the mesosphere, followed by the thermosphere. And then, depending upon what textbook, you can even have another layer called the exosphere that is really high and goes out to where, wow, we would even think that would probably be real space, you know, we're really in space. But, oh, do you see that right there? Does anybody know what that shape is that represents? You can either call it a satellite, and it is particularly a satellite. In this case, the shape is the International Space Station. And so we think the International Space Station is in space, right? Well, it's really still in one of our layers. Yes, if you walk out, it would be space. You need a space suit, but it is one of the layers, and it's so thin that it's almost non-existent, although we can still measure it. So these layers are really, really strange in that most of it, there's mostly nothing there except in the troposphere, a little bit in the stratosphere. Now, why in the world would we ever even make those lines? Why would we change or say this one's this level, this one's this level, that one's that level? It's because of what happens as we get higher. And it's going to relate to the temperature. Okay? Oh, wait. Stop. Okay. What happens if you get in a car and let's say it's, you know, this temperature outside and you drive up a mountain, okay? And so you're in shorts, you're in a short sleeves shirt. It's really hot when you start, but when you get at the top of the mountain, you get out of the car, what do you feel?
It's cool in the winter.
Yeah, it's cooler when you get higher, okay? That's what we know. As you get higher, it gets colder, all right? That's something that in the troposphere works all the time, and the higher you go, normally the cooler it is, all right? That is what you might think happens all the way to space, but it doesn't. This is why we have different layers. What happens in the troposphere, here's where we start. So this is temperature in Celsius, and we're not in Europe, so we don't ever measure that way, but this is how most of the world measures it. So in Celsius, the average temperature sits right about here. As we get higher, this is the height, the temperature gets lower. And it can get really frigid, minus, okay, 60 degrees or so. But what happens is there's a time at which, as you go higher, it doesn't get any colder, okay? At that break, when this happens, that's when we made our decision line where the troposphere ended. The behavior of going up and it getting colder stopped. All right? And then what happened is really weird. In the stratosphere, it starts getting warmer as you go higher. That's really weird. There's a reason, and we'll talk about it. And at a certain time, or a certain height, the temperature is almost the same temperature as on Earth. So it's relatively very warm, okay? That's weird. And then it started cooling down. So we made a line between what happened here, where it kind of leveled out and was warm, almost the same as the surface. Then it started getting colder again, okay? And it got to a bottom, and it leveled out. That's where we made the new line. And then it starts getting warmer, and then all of a sudden it gets really hot. much hotter than the surface of the Earth. And that's really strange. Now, right up here in the thermosphere, okay, thermo meaning heat, it's the sphere of heat. What is actually happening? Well, remember the sun is shining, okay? And as the sun shines, it gives off light, and that's fine. But there's also not only light coming off the sun, but also stuff. Stuff is ejected off the sun, and it's going in every direction. And as the Earth hits that stuff that's coming off the sun that is very fast, what comes off the sun is ions, charged particles. The stuff from the sun hits the Earth's atmosphere, and that interaction makes it hot. And that's why it gets really hot at the edges. It's because we're going through the stuff that is being shed off of the sun. All right? And so the way the temperature changes define the troposphere line, the stratosphere line, the mesosphere line, and the thermosphere. And so they just behave differently, what the temperature is as we go higher. A normal air pressure that people use in weather reports is this, 1,013, what we call millibars. And we consider that to be normal, and we consider that normal is measured at sea level. And so that is normal air pressure, how much is supposed to be pushing on us. Now, there is air pressure. You don't feel it right now. But there are times that you do feel it. And if you've ever taken an airplane trip, okay, and you go up, what happens to your ears? They pop. This is why. Right now, there is air inside your ear, okay? And the air inside your ear is pushing out with pressure. Okay, you don't feel the pressure inside your ear because it is equal to the pressure that is pushing on your ear from the air outside. Okay, and what happens when you go up in a plane or you drive up a mountain is that you are going above a lot of the air, so there's less air on top of you, less pressure on top of you. But inside your ear, the pressure didn't change. Outside your ear, the pressure gets less. So there's a push from the inside out, and you feel it until you chew gum or you yawn or you plug your nose and blow. And what you do is you allow a little bit of air to rush out from inside your ear, and you become equal again. Then there's no more pressure. Pressure difference, so you don't feel it. And so it's there all the time, you just don't feel it all the time. You only feel it if it changes. And so you can actually feel the differences. Now, I told you it was much, much more concentrated at the ground level than it is as we go up. And it gets thin very fast. And you know, they talk about thin air. Okay, well really it has gotten thin. And so normal pressures are 1,013, all right? Now the tallest mountain is Mount Everest. It is 29,028 feet or 8.5 kilometers, okay? At the top of Mount Everest, there are records for climbing Mount Everest. One records with oxygen tanks. There is so little air, so little oxygen that if you aren't conditioned and you were just dropped on the top of Mount Everest, most of us would pass out immediately. Okay? But a lot of climbers will live close to the top for a while, allow their bodies to become acclimated to that level and then climb. And so there are records for ones without. Why in the world is it so low, or how low is it? Okay, well, take a look at this. If you want to even think half of the air, that would be about 500. That would be about right here. At about 5 kilometers, you're already over half of the air. Half is below you, half is above you. If you go back to the list of spheres, 5 is still in the middle of the troposphere. We haven't even got to any of the other spheres, and already half is below us. So at Mount Everest, we are about 2/3 below, and only 1/3 of the air is above us. And it falls off very, very quickly. Very little of the air is at higher altitudes. All right. Well, how do you know if you're going to pass out if you actually were dropped off at the top of Mount Everest? Well, a lot of airline flights go somewhere between 31,000 and 37,000 feet. And during the explanation of safety, if the cabin loses pressure, what happens? The thing drops down, the mask drops down, and it says, before you help somebody, what do you do? Put your mask on first. You don't put the mask on the child and they're awake and then you pass out, because the child can't reach it and help you. But if you put your mask on first and the child passes out, you're able to get that onto the child very quickly and they'll recover with no ill effect. Although if the child is awake and then they see mommy and daddy pass out and not wake up, that could be pretty traumatic for them. So the instructions are important because at that height, there is so little air in the cabin, which means the nitrogen goes down and the oxygen goes down. Our blood is not able to take the oxygen and we can pass out. And so going up not too far up actually is a function of how much air is there. Before we had airplanes that were pressurized, meaning they pump air in and they keep it at a high pressure, people were in planes that were just open to the air. There was a limit to how high they could go because they would also pass out without extra oxygen. The two lower spheres, the troposphere is where we live. We'll talk about weather, and we'll spend a lot of time on weather. Most airlines fly within the troposphere through the troposphere itself, and then some airlines can even, and some flight can go up into the stratosphere. The stratosphere, we really have no clouds and weather. And if you can get very, very high up where there's no clouds and no weather, the flights are a whole lot less bumpy. And so pilots do like to fly very high for comfortable rides. In the stratosphere, we have a layer of gas that is important for us called ozone. All right, so we've got nitrogen in the air and we've got oxygen in the air. In the stratosphere, there's a certain amount of light energy that hits the oxygen. And remember, oxygen is one of those diatomic molecules. Well, the light hits it and breaks it apart into a single reactive oxygen. Okay? If that oxygen was around you, it would be very bad for your health. Okay? It would react with you, and actually reactive species of oxygen is one of the theories of why we age even when our cells are always continually being replaced. Well, that reactive oxygen reacts with another oxygen and creates this special version of oxygen called O3, ozone. Okay? Ozone is both deadly and protective. Okay, that's weird. Ozone, if created like right next to you, is it destroys living things. We actually use ozone in some systems to treat pool water, where they'll bubble ozone through and you don't have to use as much chlorine. People like that. but it creates the ozone gas, which is poisonous to you. You might have smelled ozone behind some electronics that have lots of electricity. Sometimes very high voltage things may react with the oxygen and make this really weird smell. As you're smelling it, you're killing yourself because ozone is being made in really low concentrations, but it's not great. So if ozone was around us really close, it kills biological things. But it is protected of biological things because of where it is actually produced, up in the ozone layer, because ozone has the perfect shape to absorb a certain type of energy, and it's called the UV energy, okay? And if you go out on the beach, what do you put on? Sunscreen. That protects you from UV rays, because the UV rays are the ones that will burn you or make you tan. Well, make you tan is like cooking a turkey too. You get browner, right? But it's not necessarily doing good things to your skin. All right? So let's take a look at the ozone layer real quick. Ozone is a layer that is in the stratosphere. Now, the video indicated that there were about 3 molecules of ozone for every 10 million molecules that are in the air. That doesn't seem very thick at all. And it really isn't very thick. But that level of concentration is just enough to absorb most of the UV radiation on the surface of the Earth. Now, we go outside in the sun and we put on sunscreen to protect us from the little tiny bit of UV radiation that gets to the surface of the Earth, because UV radiation can burn us. And quite frankly, some of the energy can hit our DNA, change our DNA, and can possibly cause diseases. One of the most serious would be cancers. Without the ozone layer, our first line of defense and our largest line of defense would be gone. The CFCs that are produced are chemicals that had been manufactured for a long time, mostly in refrigerants, and we didn't know that they were doing anything bad. But if you put it out in the atmosphere, and if one of these gets broken down, the chlorine of one of the gases could break down up to 100,000 of the ozones. And remember, there's not a lot up there. So a little bit of this pollution can rip a lot of this material out. Yes?
So in the video, it talked about how the poles were the thinnest, but the CFCs were being produced in the northern hemisphere. Why does it direct?
Okay, so the question was, we're producing the CFCs in the industrialized countries, which were like in the middle of the world around the equator, but why is it affecting the poles much more than where they're being put off? All right, here's the problem with the Earth. We think of the Earth as a sphere, a ball, right? Round? Yeah, we're kind of round, but because we're spinning, we're kind of squished, and so we're a squished ball. What happens is there's a bigger amount at the equator than we have at the poles. So what happens is the atmosphere is much thicker around the equator than it is at the poles. The CFCs get mixed up in the entire atmosphere. And the reason why it doesn't affect the middle as much is because there's much more there. The air is actually thinner at the top of the world and the bottom of the world. So in proportion, we see the effects more at the top and the bottom, although they are indicators of what might happen later. So this is one example of laws that were passed in an agreement on a global scale that went into effect to reduce the production of these particular chemicals. And so at one point in time, there was old refrigerant and new refrigerant. And this is in not only air conditioners, but all of the refrigerators and a lot of different things. And so we changed all of those formulations to have less of the bad chemicals to be released in the air. Now, was one good thing about this, about ozone, is that it is naturally being created by the sun itself. And so what had happened was we were creating so many chemicals that we were actually destroying more ozone than the sun was creating ozone. So we got less and less and less and less and less. But once we stop producing large amounts of this chemical, what happens is we're still breaking down ozone, but now the sun, its rate of creation of ozone is becoming larger than our rate of it being broken down. And eventually, over time, we should fulfill or fill out those particular layers, and those thin places should fill back up. What might happen if we completely lost our ozone layer? You get burned more quickly, and a lot more cancers would be caused. And so if we didn't stop our process, then you would burn like this. You walk out, you're out for 2 minutes, and you would be burnt like you were out for 6 or 7 hours without any sunblock. It would be that kind of thing. So why in the world are the ozone holes concerning, but not so much of a hazard right now? Well, where the law is now, the law is trying to address that. But why do we not see a lot of deaths? Because there are thin places in our ozone.
Most of the thin places are uninhabited.
Correct. There's not a lot of people living on the North Pole, and there's not a lot of people living on the South Pole. But if you do live there, like scientists who go down to the South Pole to do research and they have bases down there, they have to wear sunscreen all the time, not just as a precaution, but because so much energy is coming down there, that if you don't have that, you don't have the ozone layer and another protective layer, you could hurt yourself very quickly. And so because of where they are, it hasn't affected it as much. If by chance the ozone holes were at the equator, then that would have affected large populations. We probably would have responded much more quickly. The two upper spheres, the mesosphere and the thermosphere, are so thin that at some point in time, we probably think we're in space rather than actually in a layer. And so the International Space Station is actually in one of the layers. It just feels like space. And so we can take a look at those. And there's not much known about them because there really isn't that much there to interact with.